It should be up here.
Ah, there it is. Okay, thanks. Great. All set.
And if you need the speaker,
Okay, I'll talk about it. Okay, so first I'd like to thank the organizers for inviting me to this event today, and also for the opportunity to honor with you Dr. Rostrup Nielsen. His research has certainly had a major impact on what we've been doing, especially in areas like steam reforming, hydrogen production, syngas. So one of those times we picked a topic related, which is water gas shift. It used to be called steam reforming of CO. And today we'll look at how we might improve platinum zirconia water gas shift catalysts using dopants such as yttria and sodium. And they work in very different ways, as I'll show. I'd like to also acknowledge my coworkers, Michela Martinelli from the Polytechnic University in Milan, and my coworkers at CAR, and of course the supervisor, Brett Davis. So really the recent interest in water gas shift over the last couple of decades has really been in trying to advance fuel cell technology. So basically what we've been trying to do is to reduce the size and volume of fuel processor for portable power mobile applications. And the conventional low temperature shift catalyst, and here we are talking about low temperature shift where we're taking about 3 to 5% CO and converting it to below 1% CO levels, which could possibly be handled by a preferential oxidation cleanup system or selective hydrogenation. And the conventional catalysts have some problems for fuel processor applications, problematic transient response curves to changes in feed composition and temperature, also pyrophoricity, deactivation problems in excess steam, and preconditioning steps. So for, again, the last couple of decades, researchers have been looking into new catalysts based on partially reducible oxide. And in some cases, the reduction is really very small, confined to defects such as oxygen vacancies on the surface, as well as small amount of precious metal motor, which is used to facilitate reduction and also, as I'll show, participate in the mechanism. The most recent research has been on trying to improve these catalysts, and we've had some pretty good success with doping calcia into ceria to improve its reducibility. Today we'll look at doping zirconia by yttria. And then we'll also look at another kind of dopant, electronic modifiers. So to understand how the dopants work, we first need to look at the families of mechanisms that have been proposed for water gas shift on these kinds of catalysts that rely on the synergy between the metal and the partially reducible oxide. And so on the right we have the redox mechanism family. And I show an example here where CO is hooked on platinum, reacts with the ceria, and reduces the ceria. Really it's removing an oxygen atom from the surface, and then water then reoxidizing the ceria and liberating hydrogen in the process. And so in this mechanism, the ceria is cycling through the +3 and +4 oxidation states at the surface. Then we have a family of associative mechanisms which involve absorbed intermediates such as formates or carboxylates that have also been proposed, even oxalates. And in this case, the defects are also involved. Water is associated on the vacancies to generate bridging OH groups, which then react with CO to form the associated intermediate. And this mechanism, which was proposed by Shido and Iwasawa in the early 90s to be operating, in the rate-limiting step, which is facilitated by steam. You can see that the steam is actually participating in the rate-limiting step of the decomposition before it undergoes dehydrogenation. Also, the metal is involved, so this is occurring at the metal support interface and liberating hydrogen and CO2 in the process. So you can see there are some similarities actually between these mechanisms. A lot of people talk about the differences, but similarities in both mechanisms. Defect sites are involved for activating water, and in both cases the metal at the metal support interface is participating in the mechanism. So the aims of this work are how can we improve these kinds of catalysts? And we've been working a bit with zirconia over the last several years off and on. And one idea is to dope yttria into zirconia, where we're replacing zirconia, which is +4, with yttria, which is +3, and then to maintain charge neutrality, you have oxygen vacancies introduced into the catalyst. Another possibility is, since we have oxygen additives involved in the redox mechanism, and we have absorbed intermediates which are bound by oxygen to the surface, we might be able to strain the zirconia such that we improve the oxygen mobility. And then the other idea is to use electronic modifiers, such as alkali metals, to electronically modify the intermediates in a favorable way. And this is based on a discovery by Honda and also some characterization work that we did in collaboration with Honda several years ago. So we looked at zirconia supports doped with different yttrium loadings, and also we looked at doping sodium to 0.5%. The catalysts were prepared by co-precipitation of the respective nitrates, zirconium nitrate and yttrium nitrate. And then we collected the solids by filtering, washing, and then drying and calcining. And then we added the metal by incipient wetness impregnation using tetramine platinum 2 nitrate as a salt. Pretty standard preparation method, drying and calcination at slightly lower temperature. And then we investigated the catalytic properties by a number of characterization methods, including X-ray absorption spectroscopy and infrared. And we carried out water gas shift activity tests using a fixed bed reactor under conditions which would mimic the low temperature shift feed for a fuel processor, except we did not include CO2 just for ease of analysis. So the surface areas we doped with yttrium passed through a maximum at about 50%, and the core radius passed through a minimum. When we added platinum, the catalysts that had high yttria doping were sensitive to morphological changes and led to a decrease in the surface area. But only minor changes were observed at low yttrium doping. We saw that the degree of crystallinity decreased as we increased the yttria doping levels. That could indicate a decrease in the crystallite size, as shown here, but it also can indicate microstrain, which is very difficult to analyze with this kind of data. We did see a shift to lower 2 theta, which is consistent with an expansion in the lattice and some macrostrain, which is what we wanted. The XRD profiles, that you want to see, but they can correspond either to cubic or tetragonal. It's very difficult, actually, to distinguish between cubic and tetragonal with this kind of data. You have to have really high resolution data. For cubic, you have single peaks for 111, 200, 220, 311, 400, 313, and 420. You have splitting, slight splitting of these peaks for the tetragonal. So we turn to Zane's, and the Zane spectra give some information. Actually, quite a bit of information. There's a small shoulder and inflection at 6 to 7 eV beyond the zirconium decay edge, which is due to some 4D, 5P orbital mixing, which allows a transition into the 4D orbitals, which is not allowed for the cubic. And also, there's a multiple scattering peak here, for about 18.037 above the edge, which is observed in tetragonal, but not cubic. At 50% doping, we should have cubic by the phase diagram, and we don't have those features. And there is a characteristic splitting of the main peak, which is consistent with cubic. So we have successfully doped the zirconia with yttrium. We looked at TEM, and these images were taken by Dr. Rishi Graham. For the undoped and 10% doped, we had significant crystallinity, as the XRD showed. But for the 50% doped, there was significant polycrystallinity, also in agreement with the XRD. And the platinum particles ranged from about 0.5 nanometer to 3 nanometers over all three. Very small platinum clusters. And we also saw a slight increase in the D-spacing for the 10% doped zirconia catalyst, which is consistent with the shift to lower 2 theta that was observed in XRD. And here you can see the polycrystallinity in the 50% doped one. You better see it. The TPR are very complicated. In the literature, researchers tend to assign, these are the catalysts without the platinum, so these are the supports. They tend to assign these peaks in 400 to 650 region to surface reduction. But really, these peaks are too large to just be surface reduction. You don't usually get very high degree of reduction of these kinds of materials. If you do a drift study, where you look at the decomposition or you look at the activation of the catalyst, you'll see there's significant carbonate removal from the surface. So these peaks are due to not only surface reduction, but also carbonate removal. There is a decrease in the peaks to lower temperature as we increase the yttrium doping. And when we add platinum to the catalyst, there's a significant shift in all of the peaks to lower temperature, and also there is an increase in the peak intensities, indicating more carbonate removal and possibly more surface reduction. And the low temperature peak, which is likely due to platinum oxide reduction to platinum metal, moves to slightly higher temperature with increasing surface area, indicating that there are also metal support interactions that probably need to be taken into account. To get a better understanding of the TPR data, we did some TPR stains, and this was done at the platinum L3 edge. And we see that the platinum oxide reduces completely by about 300 degrees, and that is in good agreement with our TPR profile. So the first peak, at least part of it, is due to platinum oxide reduction to the metal. And then this facilitates, probably by hydrogen association and spillover, the removal of carbonates and surface reduction. When we go to the higher surface area material, 50% doping level, takes a higher temperature, slightly higher temperature to achieve the complete reduction of the platinum oxide to the metal. And you can see this, again, there's a difference in the surface area there. So that's probably due to metal support interaction. We can speciate along the trajectory the different components involved in the reduction. So PTO2 to PTO and then reduction. And of course, these processes are slower for the yttrium catalyst. When we cool the catalyst down and look at the X-AS data, we can see that we have very, very small peaks for platinum coordination, indicating, again, small crystallites, small domains. And this would be the foil, the platinum foil with coordination number 12. So, and we also had to include in the fitting a small platinum oxygen support coordination as well. And so we were able to obtain reasonably good fittings, and we had very low platinum coordination around 3 to 4 for these catalysts. We also looked at Zanes for the zirconia K-edge, for the undoped, and the 50% yttrium-doped catalyst. And unlike Syria, where you see very significant changes in Zanes, the extent of reduction is much more limited for zirconia. But we do see a more significant change in the white line for the yttrium-doped catalyst, suggesting that the reduction is more facile. We also carried out XAFs of both the zirconia K and yttria K edges using the structure for tetragonal zirconia this is the zirconia foil. Tetragonal zirconia to fit the undoped catalyst after activation. And we used the cubic structure simultaneously fitting the zirconia and yttria K edges, and we were able to obtain reasonably good fit. And also we fit the yttria, which is also a cubic, and we were able to obtain good fittings for those structures. Okay, so the water gas shift activity, by doping yttria into zirconia, we were able to obtain a pretty nice increase in the water gas shift activity, especially at the 10% yttria doping level. We had higher activity for 10, 25, and 50% doping, whereas this is the yttria here. This is the platinum yttria. This is the platinum zirconia here. And at the high yttria doping levels, we had lower activity. So we wanted to look a little bit more about what was going on with the 10% yttria doped catalyst. So we removed the carbonates and steamed the catalyst to form the defect-associated OH groups, and we carried out CO adsorption to form formates at those sites. Now, as I said, without the presence of water, the formates are quite stable. So we can look at those in the absence of steaming. And what we see is here's the yttria-doped catalyst. We see that the formate CH stretching and the OCO asymmetric and symmetric stretching bands are significantly higher than on the undoped catalyst. And here you can see the platinum CO is pretty much the same on both catalysts. So the results suggest that we did indeed increase the number of defect sites in the yttria-doped catalyst, and we have higher density of the defect-associated OH groups. We take the ratio of the ratios, formate to platinum CO, or yttria-doped over that, over undoped. You can see the increase here. Now, then we subjected the formate to steaming at very low temperature. Here at 130 degrees, and you can see the formate is decomposing on both catalysts. But the decomposition rate is faster for the yttria-doped catalyst, and more significant as well. And of course, we have more rapid formate decomposition when formate is at the interface. So the formate here is most likely on the support away from, when we get out here, it's more likely on the support away from the platinum particles and have to diffuse to the platinum in order to decompose. So this faster rate suggests perhaps an improvement in the oxygen mobility. surface oxygen of the wafer, resulting in a higher fluid. And if we carry out steaming for a specific set time, and then we compare the catalyst, we did see that there was a greater fraction of formate from the initial that reacted on the yttrium-doped catalyst relative to the other. Okay, let's look at sodium doping now, which is quite different. Here we prepared catalysts with 2% platinum, similar to what we had done previously with the work with Honda. Here we have zirconia, yttrium-doped without sodium, and here we have TEM images with sodium. And you can see here that without sodium, even though the domains on all catalysts for platinum range from about 1 to 1.5 nanometers in this case, we do see some agglomerates of domains without sodium, whereas here, the particles are more dispersed. By putting sodium on the catalyst, initially the catalyst will have more carbonates. We observed that in drift spectroscopy. That's probably why we see these more intense peaks during hydrogen TPR for the sodium catalyst relative to the undoped. Here when I say undoped, I mean without sodium. Okay, so here we have the effect of sodium and yttrium doping on water gas shift rates. So here's our undoped platinum zirconia catalyst. This is the effect of yttrium. At 2% platinum levels, the effect is not as significant as we saw with the 0.5%, but nevertheless there is an effect. This is the effect of the sodium. It's really a significant change. And of course the best catalyst here has both sodium and yttrium doping. Remarkable change. So what is going on with sodium? Well, as I mentioned before, when we probe the defect-associated OH groups with CO to form formate, we had a higher intensity when we added yttrium, indicating increased number of defect-associated OH groups. When we add sodium, there's an electronic modification of the formate, where there's a weakening of the CH bond of the formate. Now, back in the early 90s, based on some kinetic isotope effect studies, Shido and Osawa strongly suggested that formate-CH bond breaking was the rate limiting step for water gas shift. And of course, that's been highly debated, but this weakening is certainly consistent with that viewpoint. So what we did was we carried out some kinetic isotope effect studies of our own, and we switched from deuterated water to H-labeled water for both the undoped catalyst, which is shown here, and the sodium-doped catalyst. And we should see a change in the rate if the CH bond breaking is the rate limiting step. And we certainly do see a change because the bond is, the CD bond is stronger bond than the CH. But if we're weakening the CH bond by alkali doping, then we should see a decrease in the kinetic isotope effect. And we do. We see a decrease from about 1.4 for the undoped to about 1.2 for the sodium doped. And to probe that more, we also looked at steam-assisted formic acid decomposition, which should also pass through formates. And this is the undoped here. The kinetic isotope effect is 1.4, just like in water gas shift. And when we added the sodium, there was also a decrease in the kinetic isotope effect from 1.4 to 1.2. So certainly it's in favor of formate mechanism. So in conclusion, we prepared yttrium-doped zirconia oxide materials with high surface area. Platinum addition improved both the extent of reduction and carbonate removal, and facilitated reduction as well, shifting peaks to lower temperature. We were able to increase the number of defect sites for water activation by doping zirconia with yttrium. And the higher concentration of defects, of course, was responsible for the higher intensity of formate bands when we probed with CO. The effect of sodium doping is very different. It seems to be an electronic modification leading to a weakening of the formate CH bond, and that accelerates its decomposition rate. And the kinetic isotopes effect studies that we carried out are consistent with the operation of the formate mechanism, although certainly other reaction pathways could also be occurring and cannot be ruled out. And I'd like to acknowledge Commonwealth of Kentucky, the Italian Ministry of Education for the scholarship of, now I should have changed that to Dr. Martinelli, and also US DOE for access to two of the synchrotrons here in the US. And these are some of the references that I use. Of course, if you're going to go into hydrogen production research, you're going to want to start out with the papers of Dr. Rostrup Nielsen, which will help you light the way. And I'd be happy to answer any questions you might have.
Questions? Well, I guess everyone, oh,
Yes, very useful. So I'm wondering, are you sure what the active species of platinum during the reaction condition? Is the platinum or platinum class of this kind?
Well, there have been some studies done on related catalysts using synchrotron radiation, where during water gas shift they see reduction of the metal to the metallic state. But there is a debate, an ongoing debate about the actual oxidation state of the metal.